Hey everyone, welcome to University of Winnipeg Chemistry. I'm Dr. Carroll. We're looking at the first screencast today for Chapter 16, Applications of Aqueous Equilibria. And before we get there, I just wanted to talk about the pKa and pKb, what that means. Let's say we have two acids. Let's say HA is 1 by 10 to the minus 4 and HB is 1 by 10 to the minus 6 for values of the Ka. So they're both weak acids. They have Ka values, and those values are less than 10 to the minus 2. So Hb is the weaker of these two weak acids. Now the pKa is minus 1 times the log of the Ka. So for the first one, it is, well, I don't need to calculate for that. I can just know that that's 4, right? Log to the base 10. And for Hb, it is 6. So the smaller the value of pKa, the stronger the acid, if we, relatively speaking. Okay, so that's just one point that I should mention. We're going to use acetic acid in this chapter a bit. Acetic acid is right in the middle there, HAC, 1.8 by 10 to the minus 5, and the pKa of that is, I'm going to take the log, I'm going to clear it. The log of 1.8 by 10 to the negative 5, and I get 4.74, negative log. And that 4.74 is a pKa of acetic acid. So another thing to note is that, and I mentioned it, but a bit more I should mention it here, a strong acid like HCl, its conjugate base is Cl minus. So HCl is a strong acid, Cl minus is an extremely weak base. Okay. If I were to look at HA's conjugate, and going up here, I would get A minus, and HB, I would get B minus, and HA, the value for KB is KW over Ka because it's the conjugate. So A minus, the conjugate, so I take 1 by 10 to the minus 14 divided by 1 by 10 to the minus 4 is 1 by 10 to the minus 10, and the KB equals 1 by 10 to the minus 10. So my pKb is the negative log of negative 10, and it is 10. And look at this, pKa plus pKb equals 14. So that comes in handy sometimes, which is really pKw, isn't it? And the conjugate base of HB is B minus, so that will be 1 by 10 to the minus 8, right? 10 to the minus 14 divided by 10 to the minus 6 is 10 to the minus 8, and so my pKb is 8. So the conjugate is still a weak base. So the conjugate of a weak acid is a weak base. It's not as strong. Some people think they're trying to get some sort of matching symmetry here. They say, oh, well, the conjugate base of a strong acid is a weak base, which is true. And then they'll say the conjugate base of a weak acid is a strong base. And that is not true. We don't have that kind of matching symmetry thing here. The conjugate base of a weak acid is still a weak base. So I just wanted you to look at that, be clear on those terms, because we're going to be using them a bit in this chapter. So let me go to the fancy picture. This is page 770. The pictures there about red blood cells are talking about a buffered system to keep us alive. So buffers are important stuff, and that is what we're going to look at in chapter 16. The first bit is called buffered solutions. We're going to look at how to make them and the buffer capacity and what they do and how they help keep pH non-varying very much. Okay, pH can always change when something's added, but not change drastically. So that's what buffers do. We have buffers in our stomach, so the pH of the stomach juice, the HCl or the gastric juice, doesn't vary lots. If it varies lots, then we're in trouble. Then in 16.3, we talk about acid-base titrations, and you may be happy or not happy, I don't know, but section 16.4 and 16.5 are not talked about. So we omit 16.4, 16.5. Why did I choose this lousy color? I don't like that color. Let me go back to a nice, there, that's better. Okay, so we're going to calculate the pH of a buffered solution using something known as the Henderson-Hasselbalch equation. You can look up the spelling. I call it the HH equation, or the David Hasselhoff equation. There used to be a show called Baywatch with this lifeguard named David Hasselhoff, and then he was also in the show Knight Rider with this talking car. Anyways, he was an actor from the, gosh knows, was it the 90s? I don't even know. You don't need to know. Anyways, it made us laugh. He's also in SpongeBob SquarePants, I think. But anyways, so that's what we're going to look at. pH of blood, you can look at that for motivation to talk about the buffers. So you have to have, in a buffered solution, you have to have a close control of a pH. That's the point. The pH of human blood drops below 7 or 7.8, bad stuff happens. So chemical equilibria work in the blood and hold the pH within a narrow window. A buffer solution protects or buffers the solution against pH variations. Sometimes you have two powders that you mix together to get a buffer, sometimes a powder and a liquid, sometimes two liquids. There's a variety of ways to make the buffers, but the important point is that buffers are made by using an acid and its conjugate base in almost all styles of buffers. So a buffer solution contains both a weak acid and its conjugate base, or weak base and its conjugate acid, has major species in a solution. So if I'm talking about an acetic acid, HAC, sodium acetate buffer, well, it's only the AC minus part that's important. So this is one common buffer, HAC, AC minus. Another one is NH4 plus, NH3. If you want to have an acid buffer, HAC, AC minus is a good choice. Base buffer, NH4 plus, NH3 is a good choice. And there's a whole bunch of others. And so there's two components in a buffer system, and there can be fancier kinds, chains of them and things like this. So the reason why we need two parts is because you need two lines of defense. So a solution has to react if you have hydronium ions coming in. So that would be a base. The base part of the buffer would react to try to consume incoming hydronium ions. And you also have to have a acid line of defense to counteract incoming bases. Okay, so a buffer solution contains both a weak acid and its conjugate base. If you have a strong acid, then the conjugate base won't be in large enough amounts to try to attack incoming acids. So that's not a good choice of buffer. And so here we have example 16.1. Solution contains 0.125 moles of solid sodium acetate dissolved in 1 liter of 0.25 molar acetic acid. Determine the concentrations of everything. So let's jump straight down to what's important. And oh, someone's fixing something in the house. That's just great. Okay, so we have acetic acid, and that's Ka. We have the acetate, and it's Kb. It's the conjugate base, so it's 5.6 by 10 to the minus 10. There's acetic acid, Ka, that's its value, great, okay. And so initially, we have two sources in our ice diagram. We have the acetic acid, which is 0.25 moles per liter, and in 1 liter we have the acetate dripped in, powder dissolving in 0.125. So at equilibrium, we are going to have a Ka, if we're focusing on the acetic acid, right, the way we have it set up, but we also have acetate to begin with. So Ka is the H3O plus times the CH3CO2 minus over the CH3CO2H. And we're going to make the approximation because the initial concentrations are much larger than KEQ. X is negligible compared with the initial concentration. Okay, so my Ka, I want to isolate for X. I want to find out how much H3O plus there is. And it turns out to be 3.6 by 10 to the minus 5. So that's pretty small, which means the initial amounts that you put in of the acetic acid and of the acetate are pretty darn close to the equilibrium amounts. Okay, so that means that that's just showing that we're getting ready to look at a buffer case. For a buffer, here's an important point. The acid and its conjugate base should not differ by more than a factor of 10. Okay, so one shouldn't be 10 times more than the other. Okay, so now I need to look at all this here. I'm going to do my famous, I made this up myself, it's a hockey analogy, so showing how a buffer works before I go to the example 16.2. So I'm going to go File, New, and this isn't in your book, it's a Carroll original here. I'm going to go to the image, canvas size. Oh, let's do 130. We need to see a little big picture here. Okay, so let's say we were looking at the buffer where you had your acetic acid and your acetate. Okay, and so you have a hockey goalie here. Okay, and gotta have a mask. All right. Okay, and maybe it's Connor Hellebuck or something, and glove save, stick save. Okay, I don't know what his number is. 29 maybe, 31. There's his skates. So he's the buffer. In comes a slap shot. So it stays along the ground, and let's say it is H plus. So H plus is coming in along the ground. Connor Hellebuck has to stop it using his stick. He's not going to bend down all the way and stop if it's on the ground with his glove, try to smother it. Well, maybe he'll try that, but usually he won't. So in comes H plus. So it would be the AC minus. So the acetate would represent the wood in the hockey stick. Okay, so the acetate would absorb the incoming H plus. So you get H plus AC minus goes to HAC. So you're going to have a little bit of splinters of the wood taken off because there's going to be less AC minus than there was before, but the H plus can't do as much damage. It is absorbed by the AC minus. So that is the buffering effect of the AC minus if your incoming shot is a acid. Now let's suppose instead we had a base coming in, and a base was a wrist shot. Okay, so you have a strong base coming in, hydroxide, obviously a strong base, so it's a wrist shot. So the goalie is going to try to stop it using his glove, and incoming base, well, you stop that by partially neutralizing it using a strong acid. So we're going to have HAC is the strong acid, using a weak acid, sorry. So HAC is a weak acid, which is going to absorb the OH minus. You're going to get HAC plus OH minus goes to H2O plus AC minus. Okay, so the glove is going to start wearing thin a little bit because it's going to be absorbing the OH minus and changing a bit into acetate. But again, it's not a radical amount. So the goalie literally needs 2 lines of defense to take care of all the situations, all 2 situations, slap shots and wrist shots. I want to actually one day make this with a little better, maybe some of you are good drawers, make this into some YouTube video that I would promote on all the chemical education lists and use the goalie analogy for buffers, maybe even with an animation or something. If anyone's watching this right now other than my class and wants to volunteer to make an animation of this concept, I would appreciate it. I will. I can't give you anything, but I will just give a standing ovation for that work. Okay, so I like that. Now let's go to see if we have in example 16.2, we got a strong acid, weak base buffer. Can we create that? Is it possible if we mix 5 mils of concentrated hydrochloric acid with 75 mils of 1 molar sodium acetate? Is that going to be a buffer or not? Looking at it right off the top of my head, I would say no, because I don't see acetic acid, I see HCl. But then I got to think a bit more about this, about the preparation. And maybe on the go we can create some acetic acid, which then would be the weak acid component of a buffer. So 5 mils, so plus 0.005 liters of concentrated HCl with 75 mils, so that's 0.075 liters of sodium acetate. So we got to get some information here to see what's going on. So I'm incoming strong acid. Now the book wants to use H3O plus. I would have just used H plus, but fine. So that's why you got the H2O there. And the KEQ for this process is, well, it's just 1 over the KEQ for the dissociation of acetic acid. So it'll be 1 over 1.8 by 10 to the minus 5, just to show you that this does go essentially to completion. Clear 1 divided by 1.8 by 10 to the negative 5 is 5.6 by 10 to the 4. So that works. Good. So that's my reaction. And my initial amounts, I write Ni for initial amounts of moles. Okay, so the moles of H3O plus, remember C equals N over V, so N equals C times V. So 12 molar times 0.005 liters. So I have 0.06 moles of H3O plus, and of the acetate, I got 1 molar times 0.075 liters, so 0.075 moles. Some are 6. So when they react, all the H3O plus is consumed. Okay, so it's the limiting reactant, and I have some acetate left over. Well, okay, it's a 1-to-1 ratio, so I lose 0.06 of that, and I gain 0.06 of the acetic acid. So final, I'll have 0 of the H3O plus. With the CH3CO2 minus, I'll have 0.015. And of the acetic acid, which was now created, I'll have 0.060, which is only 4 times the acetate. So the answer is yes, I really do get a buffer system by pouring a strong acid into a basic salt. We aren't separately pouring in acetic acid and mixing in sodium acetate. Here's a second method of creating this buffer by neutralizing partially the sodium acetate system with a strong acid. Okay, if you put in too much of the H3O plus, if I put in 0.075 moles, then I wouldn't have any acetate left, and we wouldn't have a buffer, right? It's like we wouldn't have a glove to make those safe, so that wouldn't be useful. Okay, let me make sure that that works. Yeah, it is a buffer. Okay, let us try this one here. Calculate the concentrations of major species present in a buffer solution by adding 1.4 grams of NaOH. The molar mass of NaOH, I've done that lots of times, is 40 grams per mole. So the moles of NaOH, and it's just the hydroxide we care about, the Na plus just swims around doing nothing. So it's going to be 1.4 divided by 40. 1.4 divided by 40 is 0.035 moles. Okay. And the ammonium chloride, 140 mils, well, that's 0.14 liters. So what was that? C equals N over V. So N equals CV. So 0.75 times 0.14. 0.75 times 0.14 is 0.105 moles of NH4 plus. So now let's write the reaction here. So you're going to have OH minus coming in, reacting with NH4 plus. So we're going to form H2O plus NH3. Okay, so the ammonium cation part of the buffer, the ammonium chloride buffer. I can't just pour an ammonium cation. I have to pour in some salt of ammonium, so ammonium chloride. The chloride just swims around doing nothing. So my initial number of moles in terms of looking at this reaction, OH minus is 0.035, NH4 plus is 0.105, then the change, and then N final. So the OH minus is the limiting reactant. Okay, that's a good thing. And then my NH3, I create 0.035. So I have essentially no OH minus when the reaction is over, 0.035 of the NH3, and the NH4 plus is 0.105 minus 0.035. Oh, screwed up there. 0.105 minus 0.035, and I get 0.07. And that looks good. You see a ratio there of 2 to 1, coincidentally. So let's just make sure that's right. Let me go to practice exercise 16.2. NH3 is 0.025 molar. Was that a 2? No, 16.2. Cl minus is 0.75. Am I looking at the wrong question altogether? Practice exercise 16.2. What have I done wrong? NH4 plus is 0.5. Oh, interesting. I'm looking at moles, right? I have to be looking at concentrations, right? Not moles, but concentrations. Oh, so this is good. So what we're saying is, I'm assuming the volume's not going to change much by putting in the solid white pellets of sodium hydroxide, but my final concentration, it's all in 0.14 liters. So the OH minus, well, that's 0 still. The NH4 plus is 0.07 divided by 0.14. 0.07 divided by 0.14 is 0.5. Okay, good. So that's the NH4 plus concentration. The NH3 concentration is 0.035 divided by 0.14. Which is 0.25. Now it also wanted, you do have some Na plus still swimming around, right? The Na plus swimming around is 0.035 moles. And that's in, that concentration doesn't change, but if we were asked to list it, then 0.035 moles divided by 0.14 liters. 0.035 divided by 0.14 is 0.25. Okay, so see, I'm so used to doing ice diagrams with equilibrium, and this one wasn't, it was a mole table here. It wasn't really an ice diagram, and I thought it was, and that's why I got tripped up. But I saved the day, I think. So NH3 is 0.25 molar, NH4 plus is 0.5 molar, good, and Cl minus is 0.75 molar. Oh yeah, I guess we didn't talk about that, did we? But that's also swimming around the Cl minus 0.75 moles per liter. Okay. So there we listed all the species dancing around. Molecular view of buffers, you can look at that yourself. It doesn't add any. My hockey diagram is way better than this thing here. I've looked at this before. I don't like it. It's just lots of baloney. I shouldn't really say that out loud. I personally don't like this method of doing things. So now we get into what I call the buffer equation, which is also known as the Henderson-Hasselbalch equation, the HH equation. The book has decided to call it the buffer equation. So it's going to help with lots of things, and I scrolled through the proof. You can look at it if you want. I'm going to write it on a piece of paper since I'm going to be using it a lot. So the pH of any buffer system is the pKa of the weak acid, right? We aren't talking about strong acids, plus the log of the initial concentration over the equilibrium concentration. Sorry, no, it isn't. The initial concentration of the conjugate base in the buffer over the initial concentration of the acid. And there's others, Henderson-Hasselbalch varieties, and back in the days when I would teach the MCAT prep course, they'd have these 3 different ones, and I kept saying, well, just set it up so that you only need one, right? Make it more complicated. You only need one, and that one, just make sure that you set it up so that you're looking at the Ka of the weak acid, and then the A minus will be the conjugate base. Rule of thumb, this can be applied as long as the difference in factor between the concentrations is less than 10, which means that a good buffer is going to be essentially being able to maintain a plus or minus 1 pH unit difference in the pKa value. So if we were talking about acetic acid, the pKa was 4.74. So the pH, if you're having a acetic acid buffer, so that would mean acetic acid is the weak acid and acetate is the base, that whatever you want to maintain at a given pH can't be more than 5.74 or less than 3.74. This is important in biology when you're looking at certain enzymes and they have to work within a certain pH range. So that plus or minus 1 is typical. Approximations, other things fall apart if your difference between the weak acid and the conjugate base concentrations is more than a factor of 10. So let's use that buffer equation, the Henderson-Hasselbalch equation, to example 16.4. And we have here buffer solutions with a pH values around 10 are prepared using sodium carbonate and sodium hydrogen carbonate. What's the pH of a solution prepared by dissolving 10 grams of each of these two salts in enough water to make 0.25 liters of solution? Okay, so here is the buffer equation, as the book wants to call it, and I have the HCO3 minus. I'm going to take that one as the one to focus on because it's got both of them in there, and it shows the HCO3 minus acting as an acid. So I have to get the initial concentration of the carbonate, the initial concentration of the bicarbonate or hydrogen carbonate, and then the pKa. Okay, well, let's get that. This proton transfer reaction involves the second acidic hydrogen of carbonic acid. So the appropriate equilibrium constant is Ka2, which is the second ionization. And so pKa can be found in the appendix, unless you've had your appendix removed. So it's 10.33. I'll never tire of that joke. So 10.33 plus the log of the concentration of A minus over HA. So HA, we have 10 grams divided by the molar mass, which you can look up, 84.01. Then the whole thing is in 0.25 liters, so it's 0.476. And the carbonate is 10 grams over 106 grams per mole, so that's moles divided by 0.25 liters, 0.377. And we just plug those in, and on to page 778. So the 0.377 goes in the numerator, the 0.476 in the denominator, and then we get a value of 10.23. So it's only off by a factor of 0.1. So the pH is close to the pKa, so that is a typical buffer story, and that's good. Now, if you were awake, you may have noticed something here. There's a ratio here between the conjugate base and the weak acid, right? Now, we were mixing this into 250 mils, but if we used a different volume, we would still get the same pH change, because you see that the volume actually cancels out. So if you press for time and you're mixing two powders into the same volume, the volume doesn't matter because it cancels out, right? So the 0.25 liters cancels out in each of these. Okay, so that's an example of the Henderson-Hasselbalch equation, and you can try the practice exercise 16.4 on your own. Okay, and if you have any problems, we can do it in class. So why don't we do it in class? I have no idea what day that is, but we'll do that. Okay, so that is preparing a buffer. What about the action? Oh, we're going to go back and look at preparing a buffer later on, aren't we? Okay. What about the action of a buffer? We have these two lines of defense. Okay, good. So let's do this question here. By how much does the pH of the buffer solution of example 16.4 change on the addition of 3.5 mils of 6 molar HCl? Okay, so let's get the moles of incoming acid. That's 0.119. How am I getting that? 10 grams. Why are they using 10 grams? Example 16.4. Okay, 10 grams divided by 84. Oh, okay. This is how many moles there are of the HCO3 minus and of the CO3 minus. So this is the moles of the CO3 minus, which is the conjugate base of HCO3 minus, is 10 divided by 106. Okay, so that's how many moles you have of the each of those. Now we bring in the HCl, 3.5 mils, so that's 0.0035 liters times 6. And you get 2.1 by 10 to the minus 2 moles. So you now, oh, they're going to avoid using a table. How about that? Interesting. They're going to say that because this 2.1 by 10 to the minus 2 is smaller than either of these moles, that this is the limiting reactant. Okay, so the incoming hydronium reacts completely. That's why it's the limiting reactant with, now which one is it going to react with? increasing the amount of HCO3 minus. So you're going to have your H plus reacting with CO3 2 minus to give you HCO3 minus. Okay, so that is then showing that the CO3 2 minus has gone down by 2.1 by 10 to minus 2 because it's being partially neutralized by the incoming strong acid, and the HCO3 minus is going up by that 2.1 by 10 to minus 2. So the book here is just trying to show you don't always have to use the tables. I like using the tables all the time, but here they want to show a different strategy, and good for them. Go ahead and do that. So they get the moles of HA is the initial number of moles, 1.19 by 10 to minus 1, plus the incoming HCl, 0.021, and you get 1.4 by 10 to minus 1. Now, I forget what the question asked for. What is the pH of the solution? Well, we got that. It was 10.23, and now we're making a change in the buffer. So we can use the Henderson-Hasselbalch equation. 10.33 was the pKa, like in example 4, plus the log of the CO3 2 minus 0.073 divided by the 0.14, and you end up with 10.33 minus 0.28, so 10.05. Before we put in the acid from example 16.4, the pH was 10.23. So we see that the pH has indeed decreased by adding an acid, which makes sense. This small change is a reasonable outcome for a buffer solution. Make sure that if acid is added, the pH decreases. Okay? So let's try this practice exercise together. By how much does the pH change if instead of adding that acid, I add a base? So 0.92 grams of NaOH. So the molar mass, we remember, is 40 grams per mole. You don't even have to remember. You can look it up. So I'm going to take 0.92 divided by 40 is 0.023 moles. Okay, so the moles of OH minus is 0.023. Now I'm going to use a table here because I just liked it better. So I'm going to go to example 16.4. No, you know what? They don't even. They should put a table. Okay. Well, let's see. I'm going to just wing it here. Here we go. So we got. I'm going to have the acid going in there because it's the acid which is going to be attacking the incoming base. So you get H2O plus CO3 2 minus, and so that is the equation we have. So the initial number of moles of OH minus is 0.023. The initial number of moles of HCO3 minus from example 16.4, sorry, from example 16.5 is 0.119. 0.023, 0.119, and the initial number of moles of the CO3 2 minus is 0.0943. So the change, so the OH minus gets all consumed. I mean, it has to. If it doesn't get all consumed, then you have destroyed the buffer, right? So this is N initial. My change, I'm going to lose the 0.023 of the OH minus, lose 0.023 of the HCO3 minus, gain 0.023 of the CO3 2 minus. Is that balanced, by the way? Yeah, okay. And so then my N final, 0, And then I got 0.119 minus 0.023, 0.119 minus 0.023, which is 0.096. And then I got 0.094 plus 0.023, which is 0.117. Okay. Now I could get the concentrations here, but there's really no reason to, because it's going to be a ratio here. So the pH equals the pKa, which was 10.33, plus the log of the conjugate base, which is CO3 minus. I mean, I can divide by the volume, but the volume term will cancel out, over the HCO3 minus, which is 0.096. So 0.117, 0.117, clear, 0.117 divided by 0.096 is 1.2188, fine. And then I'm going to take the log of that value, and I'm going to add it to 10.33, and I get 10.42. So that sounds reasonable, right? It's not radically different, and it's also higher than 10.33, which you want because you're dumping in a base, so the pH is going to go up. So I'm pretty confident that's right, but I'm never sure, so let's take a look. So practice exercise, increase by 0.18 to 10.41. Oh, and I said 10.42, so that was just a bit of rounding, wasn't it? Okay, then there's a picture showing all that. You can see that if I just add hydrochloric acid to some buffer, the pH change isn't much, but add it to pure water, the pH change is a lot. Okay, so here's a question I always see on tests. Which of the following sets of chemicals can be used to prepare buffer solutions? For each that can, specify the weak acid and its conjugate base. So HCl and KCl. Well, no, that won't work. Okay, HCl is a strong acid, but KCl is just some neutral salt. There's nothing exciting that's going to happen here. So that is not a possibility for a buffer. HCl and KNO2, yeah, that'll work because you'll have H plus reacting with NO2 minus to give you HNO2. So as long as you're careful and don't completely neutralize the NO2, keep the ratios of conjugate base to acid 1 to 10 or 10 to 1 within those limits, then you would get a buffer being prepared. HCl and NH4 plus Cl. No, I don't see that happening. No, I would get more HCl. I can't take this acidic salt and add an acid to it and expect to get a buffer. So that one's no good. NaOH and Na2HPO4 2 minus. Yeah, I will have the OH minus can react with the H2PO4 minus to get away one of those protons. So I'll have HPO4 2 minus and PO4 3 minus. So that's a buffer. NaCl and NaC2H3O2. A basic salt and a neutral salt? I don't think so. Let's take a look. Section exercise 16.1. Not suitable for A. Yeah, we crossed it out. B, HNO2 and NO2 minus, good. C, we said was not suitable, good. D, HPO4 2 minus and PO4 3 minus, that's good. E, not suitable. Okay. Okay, 16.1.2, I don't care about that. 16.1.3 is an important one that I want you to try on your own, okay? Struggle with it. If you have any problems, we can talk about it in class. Okay, just a bit more here about buffer capacity. and buffer preparation. Well, actually, that's, you know what? Let's leave it at that. Let's leave it at that. So because that 16.1.3 is a bit detailed. Oh, I've also lost my page altogether. So you try that one, and we'll do our second lecture. We'll go to 16.2 next time. Okay, sounds good. Good. I'm gonna go have my supper. See ya.